Hello everyone. Another day, another lecture. And today I'm going to talk about a subject that goes very deep. It goes to the heart of what we call mathematical physics. And that's that mathematics has nothing to do with physics, first of all.
All the windows are closed, there's no light there, but you're shining.
I always shine. I come from heaven.
You need a tan.
I'm going to argue today that mathematics has nothing to do with physics. And specifically that mathematics is not the language of physics.
I think that was our first topic too.
Well, we repeat it, but with a different example today, I guess. Make our point in a different way. Math has nothing to do with physics, but I'm going to argue that mathematics is not the language of physics. And, you know, a mathematician, he doesn't care if it's a dog or a cat. He just looks at speed, mass, how much time, you know, these parameters. That's what he looks at. So he doesn't care if it's a dog or a cat. And sometimes that qualitative difference between objects does make a difference in the conclusions you reach. You know, is it the same thing for a rock to go straight than to say that you sent a little disc along a chain? You get a chain across the river, you send a disc and it goes through there, it goes straight. Is that the same mechanism than just throwing a rock? There are differences. And these are the qualitative differences that the mathematicians never factor in, you know, in their calculations. And that's how they end up with black holes and dark matter and some of these weird things out there.
They'd break that down to distance traveled. They wouldn't care how it was traveled.
Right,
they don't care if it was along a wire or if it was just thrown, or they don't care about the how, it's just that it did.
Yeah, and I'm going to provide a couple examples as an introduction here. And the first one is, some of you are familiar with my arguments already. And this is a line. You know, we don't know what a line is to this day. Everybody says, well, we can't define what a line is, but we'll use it. And again, all of this is typically in the context of geometry, right? And here are some of the statements made by Herman Weyl in 1952 in his book Space, Time, Matter. And he goes through, first starts with point, then he goes into line. When he gets into line, he's got like 9 different notions of what a line is, but I pulled 3 out, which I think are very straightforward. I mean, is a line a series of apples, one point next to the other? Is a line a stick, you know, made of a single piece? Or is a line an itinerary, all these locations of a ball that just rolled by? And here you see his statement. He says, an array of points on a straight line under construction. So he's constructing his line with points, and he says, you know, he's got this array of points.
That's the apple one.
Yeah, that's the apple. They're going to go one with the other one, right? They're respective. And here the second one says, all the points which we obtain finally fuse together into a linear continuum in which they become embedded, giving up their individual existence. This description is founded on our intuition of continuity. And again, he's talking about something continues, the points lost their individuality. He's talking about a stick. And then the third one has nothing to do with the previous 2, and he says, let A be a translation which transfers the point A sub 0 to A. This same translation will transfer A1 to point A2, A3, and so on down the line. So we've got, at least he's got 3 different notions of what a line is, and no wonder the mathematicians at the end of the dissertation tells you, you know, we don't know what a line is. We can't define the word, but let's go ahead and use it. And that's how they end up saying it's a one-dimensional line. And you say, well, how can the second one there, for example, the stick, you can't imagine a one-dimensional stick. You cannot imagine a stick that only has width or just height. You need at least 2 dimensions to visualize an object. And that's one example. Here's another example, and that's also one that many of you are familiar with my argument here, and it's distance. You know, what is distance? Well, they say that distance and length are exactly the same thing. And you say, how can you say that? Is the length of the table the same thing as the distance between 2 tables? In one case, it appears, right, that we're measuring space. And in the other one, you're talking about, you know, continuous matter. At least you treat the table as a continuous object. And then the third one there, you know, it's also distance, but not distance as you would understand between 2 objects. You're talking about distance traveled. Here the ball traveled, and you say, what is the distance that the ball traveled? And you might measure it with a watch like I show there, or you can just roll the tape or count tiles. You know, you got all these different ways of measuring. Why? Because the mathematician, he's not interested in the qualitative notions. And he passes by them and just brushes them aside. And all he's interested in is the numbers. How many meters? How many feet?
Or how many apples?
Or even meters per second, because then he translates that into meters by doing some little calculation there, right? So you know, are these all conceptually the same? No, they're not. They're all different notions. And so you say, well, what is distance? Well, you know, we use all of them. And this is the problem. The problem is that mathematics only cares about parameters which do not take into consideration what object is doing the motion. Not always do they consider these things, and they don't care about them. They care about the parameters. And you say, well, Bill, why are you raising this? I thought this was a massive week. We were going to talk about mass, right? What does this have to do with mass? And I'm saying here we have a problem, because I think it was in 1911, maybe I'm off on the date. Einstein came up, Albert Einstein, a mathematician, not a physicist, but a mathematician. He came up with a principle of equivalence. The principle of equivalence states, and here we have a little diagram to show what it is, little picture. Principle of equivalence says that gravitational mass is the same thing, or apparently is very close to, depends on how we measure, right? The same thing as inertial mass. So we have gravitational mass. What does this mean? It means that, you know, when you're falling to Earth, like the astronaut there, he falls at a certain speed and he has a certain feeling in his body. And what Einstein was saying is that, you know, this matches exactly what we feel if we are accelerated. Essentially, he was saying that gravitation and acceleration are the same thing, because after all, gravitation is some kind of acceleration. So he says, you know, here the astronaut is falling to Earth, or you're falling from an airplane without a parachute, right? And he says that's more or less the feeling you would have if you were accelerated in space, like, you know, with a rocket.
Interesting enough, that's exactly what the flat earthers use to explain gravity.
The Earth coming up to you, yeah. So you say, okay, so what's the problem? Well, the problem that this is math and has very little to do with physics. You know, in Einstein, I want to clarify that, right? Einstein said that they're physically indistinguishable, and that's that statement and that notion is maintained to this day. If you ask a relativist, if you ask a mathematical physicist, you'll say, well, you know, inertial math and gravitational mass are the same. You know, we can't tell the difference, and numerically and unit-wise, they're the same thing. You know, so they don't see any problem, because to them it's just numbers. It's just quantitative. It's not qualitative. Enter the rope model of the atom and of light and of gravity, right? And we enter that, and now you see a little difference here. And I try to make this dynamic so that you can see it. Here we have our little astronaut, and he's tied. Every atom of his body, I just put one atom there in each case. Every atom of his body is tied to every atom on the earth. As he falls to earth, more ropes fan out. In other words, you have more, as my son corrected me yesterday, more effective ropes pulling on you or acting upon you. Not pulling, I don't like the word pull, but acting upon you. As you fall, ropes fan out. So now these ropes don't pull along the same angle. Now they pull at different angles, and it's like, they're acting individually on every atom of your body. On the other hand, you can see on the bottom one, the astronaut is going with his spaceship, and he's not, he's not being pulled by any ropes. His is a push mechanism where the ship is moving forward, and he receives that, he's part of the inertia for the ship. So he gets pulled back towards the seat and he moves forward, right? But there's a difference, a physical difference between these two cases. The top one is your gravitational mass. The bottom one is your inertial mass. The bottom one is simply has to do with motion. Okay, it has to do with, someone pushes you and you accelerate. And you feel that acceleration. And these people are saying, well, that's the same thing as if you were falling to earth. This shows that it's not. Because in this case, what you have is ropes that are fanning out and in that sense dragging you to earth. You don't see ropes in the second scenario. You only see them in the first scenario. Okay?
To clarify the difference you're making, you're saying that the mathematicians, since assuming... But let's assume that the rocket is accelerating at the speed of gravity, 9.8.
Yeah.
So they're saying that the
meters per second square.
The effect is the same, so the
Correct.
Qualitative difference is
irrelevant,
negligible.
or
it's irrelevant. Yeah, no, you're right.
For them, they say it's irrelevant because they say it's negligible in the sense that we try to measure both of them, and they're so accurate. They're the same that for all practical purposes they're the same. But the important part is that they say it's physically the same thing, and I'm saying here it's not physically the same thing. It's not the same thing, partly because one is a pull. The first one is a pull. The second one is a push. So they're conceptually different to begin with. But the first one, under the rope model, you have all these ropes pulling on you as you approach the Earth. You have more and more and more ropes. That's not the case in the second, in the rocket case, because here we're not talking about ropes at all as far as why you move forward. So they are qualitatively different.
If I get pulled at 10 meters per second, it's different than if I get pushed at 10 meters per second.
You know how this came up? It came up because Adrian and I, we had a talk the other day, and we talked about the torus. The Stanford Torus, I think it was in the 70s that they came up with this idea, but it turns out that this idea was already running since the 50s. Werner von Braun, he already had an idea about a torus. And
the shaver guy?
Yeah, the shaver guy, the rocket guy, the rocket. He already proposed the torus in the 55, already in 1955. He had a model. If you look on the internet, you'll find him. But anyways, the torus, the Stanford came up with a torus, and with a livable torus, and they say, look, we can have anywhere from 10,000 to 100,000+ people on the torus. And they made a little mock-up with half the torus having agriculture, the other half not having agriculture. They have the place where people live and so on. And so I pulled a little torus out here, and you can see it. You can see what I'm talking about. Let's see if I can get it up there. Okay, here's a torus, okay? And this torus is a livable habitat. I guess I'll just hide behind it. It rotates in space, according to Mr. von Braun. It rotates 3 times per minute, and that gives the people who are living on the outside of it. Okay, they're living on the round part, and their feet are against the outer part of that wheel. So they're standing with their heads towards the center of the torus.
There's a lot of amusement park rides that mimic this.
Right.
It spins and you get hit to the wall.
Right, correct. And that's essentially what this is. And so this torus is out in space, and let's assume we want to build it. Okay? What is the problem that I see here? Well, they say, well, you know, gravitational mass is the same thing as inertial mass. Well, is it?
Centrifugal force in this case.
Right. In this case, it's centrifugal force. And you're standing, you feel the 9.8 meters per second square because you're standing against the rim, you know, of this whole wheel. You're standing on the rim. And you're being pushed outwards. And here you see what I'm talking about in a little drawing. Here's the same wheel, just a snapshot of it, right? You're not being pulled by ropes or by, you know, every atom of your body is tied to every star, but you're so far away from them that it's not the ropes that are really tugging you outwards. It's the centrifugal force of the wheel that's pushing you towards the edge of the wheel, okay, of the torus. And so, you know, when you look at this, you say, and this is what I want you to take as homework today.
I already answered. I have an answer, but
I
want to bring something
he already has an answer. Okay,
yeah.
But look, this is homework, and for tomorrow, let's see if anyone can come up with and tell me if it's the same. Remember, Einstein said it's the same, right? It's physically the same, no difference. We're going to build the torus. We're going to send it out into space. We did our calculations. And we say, look, gravitational mass is exactly the same as inertial mass. No problem, okay? So the numbers match, right? Now we're going to build the torus. We're going to send it out into space. Does it make a difference if you're standing on that wheel like that little man is there, right? I hope you see him. There's a little beige man there. He's standing against the edge of the wheel. Does it make a difference if that gravitation that he's feeling comes from the push from the centrifugal force of the wheel which is turning versus if he was standing on Earth, which would mean that on the pull side there, you would have all the ropes tugging at him in that direction. Does it make a difference? Does it make a physical difference? Can you live and say, oh yeah, I got gravity. See, we got 9.8 meters per second square. Yeah, but you don't have the ropes tugging on you. Does that make a difference on your body? That's homework.
Well, I just thought of one scenario where there would be a
Hey, don't
difference.
give it up. That's homework, remember, not classwork.
Well, you can go as deep as you want into the question.
Yeah, I know.
One thing that you could do on the torus that you couldn't do on Earth is, assuming you could throw a ball in the opposite direction that the torus is moving, right?
Okay.
You throw it.
Oh, with a little man, are you talking throwing the ball towards the center?
No, not towards the center, but counterclockwise.
Oh, okay, so it's going to go around.
Yeah, but if you throw it in the opposite direction
in which the torus is spinning.
Yeah, you throw it at the same speed that the torus is spinning, right?
Okay.
The exact same speed. Somehow you have that beefy
that
arm.
curveball.
Yeah. Or you just put it in a cannon, for example. You shoot it out of a cannon at the exact same speed that the torus is moving.
Okay.
That ball would float there.
Would float there.
It wouldn't be affected by gravity in this sense because there's nothing pushing it outwards, as far as I can tell. Wouldn't it just float there and everything passing on by?
Well, hold it. Hold it. You're shooting it out, right?
Yeah.
If you're shooting it out, you still have inertial mass.
Yeah, but remember the cannon is going the other way at the exact same speed.
Oh, that's what you're saying. So okay, I see. Now I see what you're saying.
So they cancel each other out.
Okay, so you're saying the speeds cancel each other out. The cannon is spinning in one direction, or you throw a ball. Maybe the cannon is too violent; it goes too swiftly. But let's say you shoot the ball. You have this strong arm. You shoot the ball, but you're shooting at 9.8 meters per second. Well, I don't know.
No, the torus.
Yeah. It's just the speed of the torus. So you shoot the ball in one direction. You're moving in the opposite direction. The two speeds cancel out, and you're saying the ball just stays there in the middle of nowhere.
I mean, until like a pole or something.
Yeah. It's okay.
It wouldn't be affected. It would just be floating there, essentially.
Food for thought.
That's just one thing that I mean.
Well, that's another issue. Another issue is, does a fly inside an airplane.
Oh man, that question.
Does it fly inside an airplane? Does it fall? Does it feel the motion of the airplane? Does it regulate its location within the airplane with respect to the airplane, or is it flying independently of the airplane? You know, this is a question that we've discussed for a while. So take that as a second piece of homework. We'll discuss that tomorrow. Okay.
Oh, you're not going to answer the flag?
No.
No, you better answer it next time.
It's going to be a cliffhanger. Okay, that's the first issue. And
that was a lot of issues.
Yeah.
That was the 8th issue.
We got lots of issues here. Okay, and there's one more issue I want to touch, which is related to this as well, and which always troubles me tremendously. Other people don't get bothered by these things, but these things keep me up at nights. You know, I have to take aspirins for the headaches, and I got to drink too much beer to forget about it, and so on. You know, it's just a big mess. And that's this issue here. Okay, and I'll just blot my face out with it, I guess. They use in Newton's universal equation, universal gravitation, force is equal to the gravitational constant, mass times mass, and it's over distance squared. And the mathematicians, since I guess they don't care about, you know, qualitative differences either, they always put radius, the little r, and that troubles me so much. First of all, you know, that only is applicable to perfect spheres. And a perfect sphere not only has to be perfectly round, but it has to be perfectly compact. In other words, the construction inside it has to be completely uniform. If you have more iron on one side and carbon on the other side, it's not going to be uniform. It's going to be weighing more. It's going to be wobbling out there. And so you can't use the little r. That's one of the reasons you can't use it. The other one is that, you know, the Earth is oblate. It's not what is called prolate. Prolate is when it's squeezed in the direction north-south instead of sideways, like in this case, right? Here, the Earth is wider at the equator and flatter from north to south. And the numbers that they come up with is that these two are about 20 to 30 kilometers off, depending on where you measure. And so why is this important? Well, it's important because, you know, now we're going to look at the moon. And the moon is attracted to the center of the Earth, wherever the center of the Earth is, and that's the gravitational center, right? And is it the same for that moon to go around the equator as to go around, you know, from north to south? Like, for example, in the case of Uranus, you have Oberon goes north to south, goes over the poles. And so, you know, in the direction in which a planet is oblate or prolate, whichever, is important for, you know, gravity, and also for what we call gravitational mass, as well as inertial mass. Because look at this.
To the degree with which they're.
Oh, of course, yeah, of course. But imagine if you stand at the equator. So just take that line, the one that says 6,378 kilometers, take it all the way to the edge of the Earth there, and you're standing at the edge of the Earth at that point. Okay, so you're exactly 6,378 kilometers from the center of the Earth standing there. You're not going to weigh the same as in the North Pole, okay? And the reason for this, or in the South Pole, is maybe in this case it's easier. The reason for this is twofold. One is that your inertial mass is going to be affected by the rotation of the Earth. If the Earth is rotating, around the equator, right? Not we don't rotate north to south yet. maybe after the dinosaurs died, I don't know, that changed, but you're on a merry-go-round. So the Earth is pushing you out, and you wouldn't have that feeling if you're on the North Pole, on exactly the North Pole, or wherever the exact north is. You're standing at that point, and as far as you're concerned, you're just rotating, you know, in place, right? So you don't have that inertial pushing, that centrifugal force pushing you out like you do in the center at the equator. And the other issue is that if you're in the North Pole or the South Pole, you're going to be closer to the center of the Earth. There's your gravitational mass. So you have these two factors here. You have the gravitational mass, which is different at the equator than at the poles. And you have on top of that, you have the inertial mass, which is the rotation of the Earth shooting you out. If you're standing at the equator versus standing at the exact north. And so again, R2 is a shorthand, but it's a lousy shorthand. People should not use R because R is only for perfect spheres, which are also qualitatively, something mathematicians never take into consideration, which is also qualitatively, it has to be uniform. Because if it's not uniform, as the metals or whatever you have inside that sphere are different from one side to the other, then that R2 is very, very misleading. It's always better to use distance. Okay, so I just wanted to clarify that as well.
What's the name of this equation?
This is Newton's universal gravitation equation, the force equation. Gravitational constant, mass times mass, divided by, not R, but distance squared. Okay, and so I just wanted to clarify that as well.
But don't mathematicians, I mean, I'm sure they're aware of these things and they just kind of say, okay, it's ballpark figure.
Yeah, and that's the way they use R. They use it as a ballpark figure, but I'm saying, I mean, math is supposed to be accurate, right? Don't use a little r, use distance. Anyways, R is not always distance. So it's better to use distance because that is what the equation says, not R. R is an invention of mathematicians who came later, and they said, oh, we're just going to deal with round balls, perfectly round balls. And again, since they don't pay attention to things like, what is the chemistry of that object? It's perfectly round, but, maybe it's lopsided. Maybe it's got all the metal on one side of the planet inside it and nothing on the other. Maybe it's hollow on the other side. Well, then you can't use the little r because it doesn't make sense.
Is the sun perfectly round or oblong or oblate? What is it?
The sun is also slightly oblate, like the Earth. It's flattened at the poles, but again, it's very little because first it's got so much mass, right? It's got so much, so many atoms. Second, you've seen the arcs, and you've seen the magnetic field, the threads going through those arcs and curving them around. Well, these things, and you see it because they've got this filmed where you see matter, which is probably gas in some weird state, plasma, the fourth state of matter, falling towards the surface. And so, that thing is in constant upheaval, the surface. It's not a clean surface, it's not a smooth ball by no means. Yeah, and so, again, if you're going to get technical about it, you're going to go to the nitty-gritty, the sun is not a perfect ball at all, not even close.
Are all
it just looks round from far away.
Oh, so does the Earth for that matter, or the moon. But do all planetary, or celestial objects, do they all oblate? I don't know what the verb would be, in the direction that they're spinning in? I
don't know about Uranus because Uranus has a weird spin. So, and Pluto also, because Pluto describes a bullseye pattern as seen from the sun. It doesn't rotate like Uranus towards the sun, right?
That's weird.
If you're the sun, this is how Uranus rotates. It rotates over its pole, slightly off center because it's not perfectly over the North Pole. It's kind of tilted, and it's like diagonal,
but it's towards us.
Yeah, but it's rolling towards us. Remember,
the coin is rolling towards us.
Yeah, and the moons of Uranus, it's interesting, they rotate in the same direction. So, it's one of the issues that I have against relativity, because relativity cannot explain three object systems. It can only explain two object systems. The Earth weighs the canvas downwards, the moon goes around it. No problem there whatsoever. But then when you get to Uranus, if the sun weighs the canvas downwards, that means that, Uranus also should weigh the canvas in the same direction, right? Because it goes around the sun. Right? But it doesn't. It pushes sidewards and the moons go around its poles. And the same thing happens to Pluto and Charon. Charon, again, describes a bullseye pattern as seen from the sun. And that shouldn't be the case, because if all planets weigh the canvas downwards, and they should, if the gravity well of the sun is downwards, and we'll call that downwards, going south, all the planets should do the same. And they don't. And that's where Einstein's relativity fails. His prediction failed. Okay, it simply doesn't work. You can't do Einstein with 3 object systems. It's impossible. But on the other hand, what it does show is quite the opposite. It shows that the rope model is quite good at it, because all the planets are being all the moons, circling the planets are being swung around by the primary, because they all twirl in the same direction. In other words, they all orbit the planet in the same direction in which the planet spins.
There's no planet going clockwise and its moon's going counterclockwise. No
or in any other different direction. Yeah. They all pretty much go like all the planets go around the sun. It's like the sun is simply, where's my little ball? This is what every one of all the planets with respect to the sun and all the moons with respect to the planets, they all, without exception, do this.
It's a whole bunch of bolas getting swung around.
Yeah, that's the way it works. In other words, that is exactly how gravity and orbiting, match each other. And you can only do that with a rope. You can't do that with warp space.
I don't know how deep you want to go into this, or if you want to go back to mass, because I have one more question about this.
Yeah, go ahead, go back to mass.
No, not mass, the spinning.
Okay. Yeah, okay, go with spinning.
Because if you're swinging a ball around...
Yeah.
How do I say this? And that ball is also swinging one around, doesn't the moon get the centrifugal force of the planet also being spun around the sun?
And there is, I think that's part of the waves that we say, that the moon has an effect on the waves of the Earth. I think that's part of it. I think when the moon goes around the Earth, it causes that oblateness also to move around, that bulb to move around the Earth, and that's part of what Newton discovered in the 17th century. He said the moon has something to do with the waves here on Earth. And Newton came up with that one. He figured out that that's what it's doing.
Probably the air too, but that was just less measurable.
Yeah.
I'm sure it has a way bigger effect on air, but it's negligible to us. We don't care which way the air goes, but if the wave comes up and takes your beach away, then that's what you notice.
Okay, so you have homework.
So what else did you want to add to the mass?
No, not specifically today, but I just wanted to wrap it up, just saying that mathematics is not the language of physics. The language of physics is illustration. You need to do physics with objects, and there is no reason you cannot illustrate the object that you're proposing, that is doing gravity, that's doing light, that's doing atom, that's doing magnetism, electricity. There should be no reason that you should not be able to illustrate something in physics. All theories of physics are amenable to illustration. Otherwise, they're not theories of physics. And certainly you cannot illustrate a black hole. What are you going to put? A zero-dimensional singularity full of mass and nothing else? Are you going to put dark matter, which is just weight with invisible weight? What are you going to put for the Big Bang, a singularity? What are you going to put for yesterday we had the Higgs field? What are you going to draw? A whole bunch of dots? And then you say, well, what are those dots? Are those particles? Well, they're not particles. They're excitations of the whatever. Because then you got to go back to particles. You say it's got to be excitation of a particle. And they say, no, it's an excitation of an excitation of an excitation. And they're just waves, and you never get to the center of the onion. You look in there and there's no onion there.
I had a few questions from Cora.
Okay.
You can't answer them because they're about general relativity. And
good. That makes my life easy. I can't answer them.
So, if the answer is I don't know, they don't know, then just say so. So the question is, first one.
Yeah.
How does mass attract mass? I understand that gravity is real, but I don't know how it works.
Well, see, this shows why mathematics has nothing to do with physics. Mass attracts mass. Well, yeah, I prefer other words. I like to say love attracts love. Now, how's that for attraction, for physical attraction? You know, can you say that love attracts love, or information attracts love, or that grace attracts intelligence?
But everyone kind of has this intuition of what mass is, you know.
But this is the problem. We're not dealing with science because we're not precise. We're not getting down to the definition. We're not saying this is mass, and if it's a physical object, you know, I can say, you know, does an elephant attract an ant, or does it pick it up, or does it step on it? And then we can all understand, because we can understand the process. Or we can say, how did the window break? Well, the stone went through the window and broke it, and the glass fell on the floor. And we all understand that explanation. Why? Because we see objects. Where it's all pictorial. Even a baby understands this. He sees the rock flying through the window, right? And window shattering is part of our experience. And you say, so the theory is, how did the window break? And do I explain it to you saying, oh, time, you know, and the force and the mass of the stone? You know, I don't use those words. I just say, look, Dad, you know, what happened was I threw the rock through the window and it broke the window.
That's a very honest kid.
Yeah, and we all understand that. Why? Because you see, I can make a movie of my hand throwing the rock hitting the window and breaking it. Okay? I don't need to know how much force, how much time it took. I don't need any of that to explain why the window broke. I'm trying to explain the window. And that's how we should explain every phenomenon of physics. Why does the Earth go around the sun? Well, you know, we have to put something in that invisible world that we can't see,
or something pushing it on the outside.
Yeah,
something's acting upon these,
and that's
either something's pushing the moon towards the Earth, or something's pulling it towards Earth.
And the first thing, that something has to be an object, and it cannot be a concept. You cannot say mass did it, because mass is not a physical object.
Okay, but back to the question.
That's only a description. You know, but that's why I'm getting back to that.
But
the guy says mass attracts mass. How do you mean mass attracts mass? Mass does not attract mass.
So you would rephrase the question as instead of how does mass attract mass, you'd say how do objects attract objects?
Right.
That would be the right way of asking that question.
And the answer to that question again is the ropes. As two objects approach, all atoms are interconnected. They're interconnected by ropes. Now we have a physical mediator, and now we can all understand the theory. Doesn't mean you believe it. It just means you understand what I'm proposing. I'm saying, if I'm going to explain how one object approaches another object, they're all connected. Every atom in each one of the two objects is connected to the other one. The closer they are together, the more effective ropes that intervene. And now you can at least visualize. You can see the movie and say, okay, I see how the two masses, the two objects came together. But when you say mass attracts mass, you know, what are we talking about? You know, we have two concepts. You can't say, not in physics, you can't say mass attracts mass.
Well, I kind of wanted to ask some questions in rapid fire, but that doesn't seem to be your style. The next question actually goes to that. What is mass? Ahead. The question from Cora goes, what is matter? If you say it is anything which occupies space and has mass, but mass is the quantity of matter, so what is matter?
Yeah, and again,
like,
because
what
they
are we talking about here?
Well, because they're defining it in terms of volume, and they're defining it in terms of mass, of how much something weighs, or how many atoms it's constituted by.
But we're still talking about amounts.
Yeah, in all these cases, we're talking about amounts. So everything in mathematics takes things to parameters that have nothing to do with physics. I don't care how much something weighs. I don't care how many atoms it has in it. That doesn't matter. That matters. That issue, those issues matter to the mathematicians. They don't matter to physics. I don't need to know how many atoms are in a rock to explain to you how the window broke. You know, for example, who cares how many atoms it's got? You know, that's something that concerns the mathematician. Who cares how fast it traveled? You know, that's irrelevant for the physical interpretation of how the window broke. And this is where we have a problem with mathematics taking over physics.
But there's a lot of, I mean, I kind of want to shoot these off in rapid fire because there's just so many questions. Another one is, why can science not explain what space, time, and mass are? there's just so many questions where people want to get to the bottom of things, and they just get the runaround. And the most common answer is always the one that I saw is it's like telling a kid to go to bed, and they keep saying why do I have to do that? And it's like you just kind of tell the person asking to shut up at some point, like stop asking why. That seems to be the most
take a course at the university and don't ask why anymore.
It's the whole why is the sky blue? You answer that, and then why that, why that. So they put everything in that context where it's like this layered onion. Where it's okay, you can ask why to everything.
And you never get to the center.
You never get to the center. So I think mathematicians who don't have concrete answers kind of put everything in that box where it's like, oh, you're just asking why for the sake of why. You don't really want to find out, or you don't really want to know. It's like playing devil's advocate for its own sake.
But you know what it comes down to, what you just said? It comes down to that they don't have rational physical interpretations, especially for invisible phenomena or phenomena mediated by invisible mediators, right? And objects or whatever. And that's where the problem is. They don't have rational explanations, and people just keep asking because they don't understand. I mean, if a person really wants to understand, he says, I still don't understand. You said, well, mass, where does mass come from? Well, mass comes from energy. And what do you mean by energy? Where does energy come from? And at some point you tell the guy, look, why don't you take a course in the university and stop asking stupid questions, right? Because you're basing one concept on another concept on another concept, and they're all a bunch of concepts. And the person just keeps being put off by more and more concepts. Mm-hmm. And we never get to the object. Mm-hmm. You say, I want to know what physical object is doing whatever. Right. And even when you get to the particle, the famous particle, they say, oh, well, the particle is not your classical particle. It's not a corpuscle. What it is a excitation of the field. And what is a field? Well, a field is a whole bunch of mass. And what is mass? Well, it's a whole bunch of energy. And just keep going around in circles with one concept being backing up another concept. And then the guy finally says, well, why don't you take a course in the university, and you'll know what energy is, what mass is, and what field is. But it turns out that these people can't tell you here what a field is, what mass is, what energy is. They can't tell you that because they never define these terms. They're all ghosts. They're all spirits. We replaced, astrology and what is it? What is it? Alchemy. We replaced them with all this nonsense of energy and mass and fields and other garbage that has nothing to do with physics.
But I think what you said also applies to the mathematicians themselves. I bet there's so many mathematicians, maybe all of them, who kind of, the ones that didn't give up at least, who always have this like
I surrender.
Tack. Yeah, that's what it is. At some point you just say, I don't know, this is the best we got. But I think they all have this like tack in their shoe. This rock in their shoe, this like, I wish I could explain this better to myself.
Yeah.
Like they also, like, even if you go to the university, you just get deeper in the runaround. You essentially get better at bullshitting yourself.
No, and what happens, and that's important also to note, is that I think the person who is relatively rational, goes to the university, takes physics, he drops out after a while because he says this is all nonsense. So those people get weeded out. Who continues? Those people who are yes men, who warm the seed, who memorize for the test, and they get a degree, and they come out and they say, oh, I'm a physicist. And the guy comes out, talking energy, mass, fields. That's what he comes out talking. The other person already quit. He became a doctor or a lawyer or who knows what. And that's also this process of weeding out intelligent people from that line of work. And second, all the people that go in there, a lot of them are mathematically inclined, and so they're
told ahead of time that it's all going to be math anyway.
Right. And so the person says, "Oh, I like math. I like to do calculations. I'm good at math." So the guy takes physics because he's good at math, and what he does all his life is just math. And they tell them up front. They said, "Look, you're not going to understand how this universe works. Don't even try, because only God knows how this universe works. So if you think you have a rational explanation, you are wrong, definitely wrong. So don't worry about the explanation, just learn the math so that you understand the ropes, you understand
your ropes.
You understand, the tricks of the trade. And the tricks of the trade have to do with math and equations and numbers, not with with the physical
Well,
interpretations.
I want to get back to the mass.
Yeah. Go ahead. Sorry.
Not mass as in religion, but mass as in
Well, it is religion.
whatever mass might be.
It is religion.
Still talking about gravity.
Okay.
If all mass and energy were at a single point before the Big Bang, wouldn't that just be a gigantic black hole? If nothing escapes a black hole, how are we here? That was the question.
Well, what they've done with a black hole, which is important in this case, is that, you know, I said it in my conference in Mexico. If a black hole just swallows things, which is what Big Bang was, you know, essentially they say it all converges to a black hole and then the thing started over again. That's what many of these people have in their minds. And you say, well, how can it spit things out if a black hole swallows things in?
If there's so much matter there pulling everything in.
Yeah, everything's pulled in. It's like everything goes deep into the hole. And so, you know, and so when they came out with a black hole, and especially, you know, when Hawking and what's his name, the guy from Oxford.
Look at me, I don't know anyone.
I forgot his name now, but you know they came.
Now that Hawking's dead, I don't know anyone.
In the '60s, they came out and they popularized, you know, black holes. And so, you know, they became so popular that, you know, the astronomers said, okay, let's look for them. And they went on with their telescopes and said, what do we look for? I mean, there's nothing there. I mean, what are we supposed to look for? So that's when Hawking came out with Hawking radiation, where the black hole spits out particles that come to your eye. So now we have a way of seeing black holes, because allegedly they don't swallow everything. They swallow part of a particle, and the other particle, for some reason, is not swallowed with it and gets split apart and travels to your eyes. Why that particle is not also swallowed in, we don't know. That's something mathematicians don't care about, because they don't care about qualitative explanations. And so getting back to your question, like, you know, here's the Big Bang. It's the original singularity. It swallowed all the mass. It's got all the mass in the universe. It's in the form of energy. And you say, well, how did that come out? Well, you know, I guess the particles that comprise mass in there split up and one came out. I mean, nobody can explain this. There is no explanation.
So I don't know.
You
don't know. That's what you're saying.
The correct answer is I don't know. Because there's no way they can rationalize how matter came into existence. And
but to get the funding, they add the word yet.
Well, they add the word. Yet. Well, no, well, that's one. The other one is they say, oh no, what happened was energy came out. Oh, okay. Now we got to solve. Energy came out. And then energy turns into mass, and mass is matter, and so on down the line.
How do people? This was another Quora question. Most of these are. How do people know that photons are massless, and not just having extremely little mass? What are the measuring methods?
They have no measuring methods. I think what they're doing here is they're calculating. Okay, they just go in there and do their calculations using special relativity, in this case, special relativity equations, and they show that if the photon just sits there, it doesn't move, it doesn't have mass. Oh. No kidding. I guess if I don't move, I guess I won't have mass either. And that's the rest mass of the photon. But when it's moving, now it has energy, right? And so now we have speed and we have relativistic mass. So we have inertial mass versus or rest mass versus relativistic mass.
Is that kind of like I've watched a lot of videos about the International Space Station, and you see like things floating around. It's really cool. But is it kind of like that, where if you have a bowling ball on the International Space Station, it essentially has no weight until you move it? If you push the bowling ball to a wall, now the wall's going to feel some weight of the bowling ball. Well, but if you just leave it there, it doesn't have any weight.
It's more or less what we covered yesterday. You have two elephants, or you have one elephant. Yeah. Okay, fine. And I like the elephants because it's very visualizable. You take
you can't miss it. You can't mistake it for something else.
So we take the elephant and we lightly, slowly with our hands, right? We put them on top of the scale.
How many people are carrying? You know how many people it takes to carry?
I'm taking this elephant's Dumbo. You know, he's got this, and you put him down on the scale, and he weighs, I don't know, a ton, 2 tons, whatever he weighs, right? So here you have the elephant sitting on the scale. And a scale next to it, you take his twin brother, who weighs exactly the same, and you drop him from an airplane.
So he doesn't weigh the same.
Well, he doesn't he doesn't weigh the same when he hits that scale. So, you know, of course, if I just put my fist against your cheek, that's going to be one pressure that you feel. If I punch you, that's going to be another. You're going to feel the weight of my fist.
Does that have to do with what we talked about earlier with the qualitative versus quantitative? They say since weight is weight, and we're just talking about different amounts, how did they explain the weight of the elephant? Do they just say that, you know what I'm saying? How
weight or mass?
Weight. Because, well, yeah, mass too.
Right.
Because if, I'm sure they hit that wall where they get different numbers for the same elephant, right? Because one is moving.
Right.
But we're just talking about quantities, and we're not saying what's really happening to the elephant on some level. I mean, I guess they do get that far in the qualitative where they say, okay, this one's moving, this one isn't. Yeah. But they always say, like, with respect. This one's moving with respect to the scale. This one is not moving with respect to the scale.
Yeah, and it all comes down. It all comes down to the fact that mathematics studies behavior. Mm-hmm. Mathematics is concerned about movement. Mathematics is a language of adverbs. It only describes how something moves. That's all the equations do. True. Yeah. They only look at how something moves. That's how you synthesize that motion in an equation. You say A plus B, X plus.
That's actually a very important point that I've never heard you say before, where mathematics only deals with adverbs.
Right.
Like a very specific...
quantitative, not qualitative, quantitative adverbs.
Only not verbs. I mean, they do kind of deal with verbs, but they really deal in adverbs.
Right. Right. They only deal with quantitative adverbs.
That's
the issue there is that, you know, so they look at rest mass, which is a behavior, versus dynamic mass. You know, relativistic mass versus rest mass. And mass itself is already a concept. It's a dynamic concept. You can't, you know, whether you count atoms, you know, quantity of matter, or whether you have dynamic mass, whatever you have there.
Or like what
mass
we
is
talked
already
about the other day with the Higgs field, where you were saying
you move again, right?
Yeah. Whereas it's not the verb; it's how much the ball that
resistance.
Isn't a ball,
how much resistance it encounters.
How much the fish that isn't a fish is pushing against the balls that aren't balls.
Right.
It's not even the actions. We don't even care about the actions. It's how much.
Yeah.
Can we measure this action?
Yeah, and that's what mass is. Mass is a quantity. Okay, mass is a quantity, and that's where you realize that you can't say I have mass like you have 2 pennies in your pocket. You can't say mass in that sense. You can only say.
I was asked that today. Someone asked me, "Did you bring time? like, do you have something to do?" After
Yeah.
Did you bring time? And it's just kind of confusing. What do you mean bring time?
Yeah.
I don't have pocket.
And I can't bring mass in the same way. You know, I can bring two coins. I can't bring mass because mass, as these people explain, the Higgs people, fanatics about the Higgs field, it's an interaction. And so what you have is an interaction, and that interaction is either increased or decreased. So if it's increased, you have more mass. Okay. And you say, what did I increase? Well, you know, it's you haven't increased something like, you know, when you have a pile of sand and you put another grain, that's not what mass is. Mass is an increase in interaction. Mm-hmm. And that's what...
something's moving faster.
That's why people say, well, what part did I increase? Well, you increase motion. When we get back to the last week or the previous week,
I love the motion
where we have an increase in motion. That's all it is, and that's what they call mass. Mass is motion.
Okay, but this leads me to the hardest question of the day, which is if you have enough descriptions, because we're only talking about descriptions. I think this is kind of the gist of what everyone's trying to do in mathematical physics is if we get enough descriptions, we'll understand it. With enough, if we get everything described to a T, it'll be self-evident. What's the wrong with that line of thinking?
Well, because a description, no matter how you turn it, twist it, or swing it, is not an explanation. An explanation has to do with causes. You have to explain a mechanism. I ask you how a car works, for example. I ask you how a car works.
Let's use the rock through a window one.
Okay. Very simple, of course. I say, okay, I threw the ball or a rock through a window, and that's how the window broke. I'm trying to explain how the window broke. And
the question is, how did the window break?
Right, and if I describe the rock and say,
and we have description.
But I can say, look, the rock was brown. Well, who cares? The rock was flying at 10 meters per second. Who cares?
But that's what I'm saying.
Those are all descriptions. I cannot explain with any of those descriptions. I can't put them together and say, and conclude, only in descriptions, how the window broke. Okay? I cannot explain, or how the glass ended up on the floor, which is really, you come later and you say, how did the glass end up on the floor? I want a theory of this. Right? And this guy said, well, your neighbor came in with a crowbar. The kids were playing baseball and they hit the ball through the window. Or Johnny came in and broke it with a rock. Well, you can come up with all different theories. And you would use different objects for the different theories. But if I describe a crowbar to you and say, look, it weighs or it's got so much mass, and it was traveling at a speed of such and such, what is that? How am I going to explain the glass on the floor with all these descriptions?
Well, that's what I'm saying.
What do I care how much energy Johnny had in his arm?
But that's what I'm saying. If we knew exactly how much every atom in this scene weighs and in which direction it's moving towards, in how much.
So far we have description.
Yeah, all description.
Yeah.
If I know exactly how much every atom weighs, which direction it's going, how fast it's going.
Yeah.
If we knew everything to a T, describe
the
situation perfectly.
Just tell me how the
this is what I'm saying. Would it not be self-evident how the
self-evident? Happen? For that you need an explanation. In other words,
at some point you have to say the explanation.
If you tell me, look, there's 10 pieces of glass on the floor. Yeah,
but that isn't enough description.
No, but
you're taking a straw man in their eyes.
No. Okay, but that's what I'm saying.
You didn't add how much every, if you add all the clues
you do it for me. I mean, you're the one presenting the theory. If you say, look, the rock weighs,
because there's a lot of detail, there's a lot of descriptions.
Okay, tomorrow we have another homework, and that's a challenge for all of you as well. If you believe that a whole bunch of descriptions, description A plus B plus C plus description C equals explanation. I want you to show me that tomorrow if you can in any way. I want to show you that you can't add up a whole bunch of descriptions and end up with an explanation.
That's a really good homework. That's a really good thought experiment.
Yeah, and so that's what I want you to do.
Really clarify.
Go ahead and add all the descriptions, see if you end up with an explanation.
But I think you kind of have to do that to clarify as clearly as possible the difference between explanation and mathematics.
Right.
Or adverb.
And math only describes. Math is a language that only describes.
You said, it only describes
motion.
Adverbs.
Adverbs. That's all it is.
They don't even talk about adjectives.
No.
They don't talk about the color red. They talk about the frequency.
Well, they do talk about dead and alive, but dead and alive under physics are not adjectives. They're adverbs because they describe motion. Right. And people confuse red, which is also an adverb if you come to think of it, because it's frequency. They
don't care about the color red. They care about the frequency that the knot balls are not moving, and then you get to the weird areas.
Okay, guys. So you have a little bit of homework. If you want to participate doing it, we'll either put it at the Rational Science group or bring it here tomorrow, or put it at the Patreon page there. And we're going to begin with that tomorrow. We'll see if we can answer some of these questions. So far we have questions. Let's find out we have answers.
Is everyone in the Patreon also part of the group?
Not everyone, no.
Because there might be some mismatches there.
Yeah, but if you want to put it in Patreon, it's fine. Either way. Anyways, we'll see you tomorrow. Same time. Bye-bye.